Okay, I'd like to welcome you all to this week's BIMR seminar. For those that don't know who I am name's Alex Seidenau. I'm the current director of the Lattice Institute, and it gives me great pleasure to introduce our speaker for today, Professor Clancy from the Department of Physics and Astronomy. So Professor Clancy got his bachelor's degree in physics from St. Francis Xavier University in 2004. Then came here to McMaster for his master's and PhD in physics with Professor Bruce Golan. Completed his PhD in 2011 and took on a postdoctoral fellowship at the University of Toronto beyond June. During his postdoc, he received a couple of prestigious awards. He was advancing fellow and also received a really prestigious John Charles Bly Prize in Physics. And then, while finishing his postdoctoral work in 2016, he took on an assistant professor position at Trent University, where he stayed for just a year before coming back here to McMaster as a neutron instrument scientist, developing some of the tools that he uses in his research today. In 2020, he was hired as an assistant professor here in the Department of Physics and Astronomy. And he's currently developing a research program in experimental condensed matter physics. And today, he'll tell us about his work, exploring Kitaev magnetism beyond the Honeycomb lattice.
Perfect. Yeah, thanks very much for the introduction. And thanks everyone for coming. It's a real pleasure to have the opportunity to talk to you today. So yeah, what I'm going to be telling you about is sort of an ongoing effort to study this interesting family of materials that displays sort of unusual magnetic properties. And hopefully by the end, I'll manage to convince you that these are materials that are both interesting for their fundamental physics, but also because they give us sort of an interesting materials design challenge as well. So in particular, we're going to sort of take a tour from the sort of classic example of this Kitaev magnetism, the Honeycomb lattice, into a few different lattice geometries and see what we can learn about these materials using synchrotron X-rays. Okay, so here's a brief outline of what I'm going to try and get through over the course of the next 45 or 50 minutes. So I'm going to tell you a little bit about what Kitaev magnetism is, how it's different from some of the conventional magnetism that we're used to, how we can investigate some of these potential Kitaev magnetic systems using X-ray scattering techniques. And then we're going to talk about 3 different case studies. So there's, again, these classic Kitaev systems that are based on the Honeycomb lattice, in particular ones that are based on iridium, sodium iridium oxide and lithium iridium oxide. Then we'll see what happens when we put these magnetic interactions onto other lattice geometries as well, including a couple FCC lattice compounds, and then our sort of most recent effort, which is looking at quasi-one-dimensional or chain-like materials. Okay, so before I start talking about Kitaev magnets, I did want to give a public service announcement. So for those of you who are interested in quantum materials or just materials in general, there are big things happening at the McMaster nuclear reactor this week. We've been working on this small angle neutron scattering beamline for many years. The instrument is almost complete. And so just this week, we unboxed the detector that goes into this instrument. It's a 25-meter long instrument. This detector you can see for scale. This is Bo Yuan, our newest instrument scientist. It's about 1 meter by 1 meter. And as of earlier this afternoon, we're even seeing neutrons. So this is really exciting. Hopefully we'll be able to start doing experiments within the next couple of weeks or months. And so if you're interested in looking at structure and magnetism over big length scale ranges, going from about 0.5 nanometer to over 100 nanometers, then this could be something that you want to check out. Okay. All right. So having said neutrons are great, now I will not talk about neutrons again. This is going to be mostly an X-ray story, and it's an X-ray story related to new quantum materials. And so one of the things that my group is interested in doing here at McMaster is synthesizing new quantum materials and studying their structural and magnetic properties with X-rays and neutrons. So how do we find new quantum materials? There's a number of different strategies we can use when we're trying to either discover new materials or design new materials. One of the things we can do is look for materials that have quantum spins. So the smaller we make our magnetic moments, the more essentially quantum mechanically they behave. We can try and design materials that are based on crystal structures that have geometric frustration. So in other words, you pick a material where magnetic interactions favor one type of alignment, which is incompatible with the crystal structure that they're based on. Okay, and this is something that we normally show with this classic picture of triangles and tetrahedra. If these magnetic moments here and here want to point in opposite directions, then it doesn't matter which way I put the magnetic moment on the third corner of my triangle, one of these bonds is going to be unsatisfied. Okay, the situation gets even worse. We move from 2 dimensions to 3 dimensions, and now 2 of my 4 spin sites are going to be unsatisfied no matter how I position them. Okay, so if we're looking for ways that we can defeat conventional magnetic order to let unusual quantum states emerge, these are both great strategies we can use. We can also look at materials that have reduced dimensionality, both in terms of their effective magnetic dimensionality or in terms of their physical dimensionality. Or we can look at materials under extreme conditions, whether that's going to really low temperatures, compressing them under very large pressures, or putting them in high magnetic fields. These are all great ways to bring out these unusual quantum mechanical properties. Okay. Another strategy that we can use is to different regions of the periodic table that are maybe less explored. And so the materials that I'm going to focus on today are 5D transition metal oxides, and particularly 5D transition metal oxides based on iridium. So one of the things that's interesting about iridium is because it's a heavy transition metal oxide, has a very different set of characteristic energies than some of the lighter transition metals that we see more often, your irons, your cobalts, your nickels, your coppers. So these lighter transition metals, the 3D transition metals, typically they're dominated by an energy scale set by electronic correlations. Okay, this is a big energy scale. It's about 5 to 7 electron volts. There are other energy scales set by the crystal electric field, the spin-orbit coupling. They matter, but they're relatively small in comparison. As you move down the periodic table and you get into these heavier transition metals, the wave functions become broader, more spatially expanded. The elements become heavier. And so these electron correlation effects become weaker. So there's less overlap between the wave functions. And the spin-orbit coupling, scales like the atomic number, it becomes much bigger. So for these 5D transition metals, the energy scales that are set by the electronic correlations and the crystal field and the spin-orbit coupling, they're all about the same order of magnitude. And so you can get some interesting competition between these different energy scales. And it can be a great place to look if you're trying to find unusual or exotic states that come about because of this spin-orbit coupling. So this is a cartoon phase diagram that sort of makes the philosophical point that we're looking for here. So what we've done is we've got a graph that's showing you electron correlation strength along the vertical side here, and then spin-orbit coupling along the horizontal. And so this bottom corner here is what we might think of as kind of, I want to be mean, but boring materials, simple metals, band insulators, things that are easy to understand. The 3D transition metals are sort of up in this range. If we crank up the electronic correlations, then we can get unusual insulating states, so-called mod insulators. If we just crank up the spin-orbit coupling, we can get topological insulators or semi-metals. So these are both interesting regimes to work at. But the really interesting or fun stuff happens if we have both big U and big spin orbit. And then you get a variety of these exotic electronic and magnetic states. So things like topological semi-metals, quantum spin liquids, topological mod insulators. Okay, so this is sort of the region that we're going to try and focus on for the rest of this talk. Okay. So one of the things that can happen when we have this strong spin orbit coupling is we can get unusual electronic properties that we wouldn't ordinarily see. And so the classic example of this is something called the J effective 1/2 spin orbital mod insulator. So the J effective 1/2 here is a total effective angular momentum. So this is basically the magnetic moment or a composite spin and orbital moment that these systems display. And this mod insulating state is one that sort of emerges unexpectedly in these iridium-based compounds. So from what I was trying to say earlier about these materials, that we expect them to have big, broad wave functions, you might expect that most of these should be metallic. When you go out and measure them, though, you find that a lot of them are actually insulators. And there's not any obvious reason why that should be the case. So this picture, which was put forward in about 2008, suggests that the way we can understand these materials is the combined effects of all these different energy scales working together. So if we start from iridium, and its most common oxidation state here, iridium 4+. Iridium 4+ has 5 valence electrons. Okay, if it's a free isolated iridium, there's these 5 degenerate levels. All can hold 2 electrons, spin up and spin down. If we put them inside an oxygen cage, that creates a crystal electric field that splits these into a T2G manifold and an EG manifold. So we get 5 electrons down here in these lower lying T2G states. And then if we apply spin orbit coupling on top of this, then that'll split these T2G states into 4 lower lying states that have a total effective angular momentum of 3/2. So these are totally filled. And then 1 doublet here that's half filled. Okay, and so this gives us what's effectively a quantum spin. To spin 1/2, it's as small a spin as we can get. So this is a great place to look for strong quantum effects. Okay, if we want to look at this in terms of the band structure, if we just have the crystal field, nothing else, we'd expect this to be a broad metal. If we apply the spin orbit coupling, still metallic, but now we've split these T2G levels into this narrow J effective 1/2 band, this broad 3/2 band. And then if we put the electronic correlations here, even if they're relatively small, they can still open up an insulating gap. Okay, and so it's, again, these energy scales all working together that gives us this unusual electronic state. So in addition to these unusual electronic properties, we can find unusual magnetic properties in these spin orbit driven systems. So one of the things that happens when the spin orbit coupling becomes larger is that we can no longer treat the orbital degrees of freedom separate from the spin degrees of freedom. So they're so strongly entangled that we have to talk about this effective total angular momentum, or J effective. And so what this means is that our magnetism takes on this sort of different, more orbital flavor. So the spins have more direction dependence, and what we get is this, what we call a J effective isospin that has the mixed spin and orbital character. Okay, if you wanted to write out this wave function, it includes contributions from 3 different orbitals and spin up and spin down states. Okay. So the interesting stuff happens when we start to put these J effective 1/2 isospins onto different lattices or different crystal structures. And so one of the common geometries that we can come across is this one. So this is a case where we've got iridium 06 octahedras that are connected by the corners. Okay, so this corner sharing geometry, we get a bond angle that goes 180 degrees from iridium through an oxygen to another iridium. And you can show, if you calculate these sorts of things, that this kind of 180-degree bond gives you what are basically Heisenberg-like interactions. Okay, so this is a geometry that we see in layered perovskite materials or bilayered materials, or the pyrochlore lattice that many of us here at McMaster know and love. And so again, the dominant interaction here for these 180-degree bonds are sort of a conventional Heisenberg-like interaction. If we change the geometry, though, if we go from these corner-sharing octahedra to edge-sharing octahedra, like this, then something very different happens. So now there's 2 exchange pathways here, one running through this upper oxygen, one running through this lower oxygen, and you can get destructive interference between these 2 super exchange pathways. And so that causes that normal Heisenberg interaction to cancel out or vanish. And what we get in its place is what's known as a Kitaev interaction. Okay, so this is a geometry that we see in honeycomb lattice type materials, or different versions of sort of 3-dimensional honeycomb shapes. This is called a hyper honeycomb lattice. This is a hyper Kagame lattice. Okay, and so in each of these cases, when the Heisenberg term disappears, we get a new term, which is Ising-like, and it's different depending on which direction we're looking. So this is because of that orbital character. Depending on which orbitals are involved along a particular direction, we get a different interaction strength. Okay, so if we go off to the left or up or down, we'll get some different exchange strength. Okay, and this can lead to something related to geometric frustration that we call exchange frustration. Okay, all right. So the interesting thing is that these bond-dependent magnetic interactions are something that folks were working on for years ahead of time. So before we had any materials where we might see these kind of interactions, they were proposed in what was basically kind of a thought experiment or a toy model. So this was what's called the Kitaev model, or at one point the quantum compass model. And it's sort of an interesting model because it's one of a small number of exactly solvable quantum spin models. And it involves these spin 1/2 quantum magnetic moments on a 2-dimensional honeycomb lattice, the one shown down here, where the interactions are highly anisotropic and bond dependent. So if you imagine sitting on one of these honeycomb sites, you can go off in 3 different directions. Each of these would have a different strength, okay? And so because of this exchange frustration, we don't get normal magnetic order setting in. Instead, we get what's called a quantum spin liquid. So this is a disordered quantum state where the spins are interacting with each other. They have long-range entanglement, but they never order, okay? And so they have unusual topological properties, things like Majorana fermions and anionic excitations. And these can be of interest to people who are looking to design topological quantum computers because they provide you with sort of a topologically stabilized way of cutting down on quantum errors, okay? All right, so I mentioned I'm going to tell sort of 3 stories here. The first is sort of to set the scene, talking about, this is a question from the audience. So this first story is about these honeycomb lattice materials. And these were important because they were the first set of materials that we were looking at to see if we could find evidence that this Kitaev picture was really being realized. So this was work that I started doing as a postdoc at Toronto. And so the main contributors are shown here. This is Youngjun Kim, Linda Grederson, who's a grad student at the time, Jennifer Sears, and Kemp Plum, all who contributed to this work. And the experiments that we did were at Argonne National Lab, Canadian Light Source, and we got some samples from various collaborators and some theory support from a group at Dresden. Okay. So we have this picture where in materials where there's strong spin orbit coupling, we get J-effective moments. And if we put them on a honeycomb lattice, there's a chance that we can get these Kitaev interactions. So as long as we've got these 90-degree bonds that we should find for edge sharing geometries, then in theory, these Kitaev interactions can emerge. But just because they can emerge doesn't mean that we can actually see them. And so the first thing we wanted to do was to look around to see if we could find evidence of this Kitaev physics in real materials. And so some of the first materials that were suggested as candidates for this Kitaev model physics were all honeycomb lattice materials, either based on iridium or based on ruthenium. So iridium, again, it's down here in 5D, strongest spin orbit coupling, quantum spins, which is good news. If you go up to ruthenium, the spin orbit coupling is a little weaker. Remember, it scales like the atomic number to the 4th power. But for the right geometry, the other energy scales can scale as well, and maybe we have a chance. And more recently, there have been some arguments that you can find Kitaev physics even up here in some of these 3D materials if you design them correctly. So you'll also see some new papers talking about cobalt Kitaev systems. So we're going to focus down here for today. And so the idea is in these honeycomb lattice materials, we've got iridium-06 octahedra. They're edge sharing, so that gives us the right bond geometry that we're looking for. And you can imagine this maps onto a picture that looks sort of like this. Okay, so you've got a honeycomb up at the top here. And because these iridium-06 octahedra are tilted slightly, you get different orbitals overlapping along each of these bonds that we've shown in blue, red, and green. So this is what gives you the potential for these 3 different interactions from the different orbital overlap. So even though in theory, we should get this perfect cancellation, Real materials, we don't expect to necessarily behave like model materials. And so even though we're looking for materials where this Kitaev interaction dominates, we expect that we might find some Heisenberg terms in here as well, our normal magnetic exchange. And also, if there's direct overlap between the iridiums, we might get these other magnetic interactions as well, things like symmetric off-diagonal exchange, sometimes called this gamma interaction. So we want to try and find or design materials that have minimal Heisenberg interactions, that have as much Kitaev as we can put into them. And we want to watch out for other types of distortions or other interactions or hopping effects that might get us away from this nice clean limit. So if we want to see if these materials are really Kitaev model materials, the easiest thing we can do is cool them down to low temperatures and see if they become quantum spin liquids. And so when we do this, do we find quantum spin liquids? No. These materials develop magnetic order at relatively low temperatures, so at about 15 Kelvin. Both the sodium and the lithium honeycombs both develop magnetic order. It's long range order. There's some sign that these are frustrated, so they order at lower temperatures than the magnetic interaction strength might suggest. In sodium, we get the zigzag magnetic order state. In the lithium case, we get a more complicated incommensurate spiral order. So if they're not quantum spin liquids, maybe they're close. The other thing we can do is we can look at the crystal structure to see if we're really close to this perfect 90-degree bond angle. And it turns out that we're a little bit off here as well. So the iridium honeycomb lattice is nice and regular. Okay, so we get sort of 3 angstrom bonds all the way around here. But there's some distortion to our iridium 06 octahedra. And as a result, the bond angles here are off by about, somewhere between 3 and 10 degrees, depending on whether we're looking at the sodium or the lithium version of these compounds. Okay, so we know that we don't have an ideal Kitaev material, but maybe there's still Kitaev physics in here if we can find it. And at this point, it sort of becomes an interesting challenge to see what the minimal model that we need to describe these materials becomes. And it turns out that if we start to introduce other terms, the phase diagrams can get more complicated and more interesting pretty quickly. So if we have sort of the simplest modification, we imagine we've got these Kitaev magnetic terms and some Heisenberg magnetic terms. Then if we tune the ratio of these two interactions, we can go from this quantum spin liquid through a sort of stripy antiferromagnetic state into a more conventional antiferromagnetically ordered state. If we throw in this gamma term, the symmetric off-diagonal exchange, then becomes even richer. And now we've got about 5 different ordered states that we can tune our way through as we change the balance between these Heisenberg and Kitaev states. Okay, so the takeaway message here is that which of these models we choose makes a big difference. And there are many of these states that are close together, which, if you're interested in making new materials or tuning new materials, gives you a lot of different phase space to play around with. So in the meantime, we want to know what we can learn about these materials using synchrotron X-rays. That's my tool of choice. And in particular, the questions that we really want to get at is, does this J-effective 1/2 picture still apply to these materials once we start to distort them? So once we start to bend our iridium 06 octahedra, that's going to change the energy gaps between these different 5D levels. And also, can we find evidence for these Kitaev interactions, either direct or indirect? And so we use 3 different synchrotron X-ray techniques, what we call resonant inelastic X-ray scattering, or RIX, that lets us look at the characteristic magnetic or orbital excitations to map out these crystal field splittings. X-ray absorption spectroscopy that lets us study the valence of the iridium and look at the size of the spin-orbit coupling. And then resonant magnetic X-ray scattering, which lets us determine what the magnetic structure is. Okay. So I won't spend too long on the technique here, other than to say that resonant inelastic X-ray scattering is sort of similar to other inelastic scattering techniques, except you tune the energy of your X-ray beam to a particular atomic absorption edge. And so that blows up one of the terms in the inelastic scattering cross-section that makes normally very weak inelastic scattering strong enough that we can measure it. It also makes the measurement element and orbital specific, so you can get some really detailed information here. So if we tune to an iridium absorption edge, all that we see is a signal that's coming from iridium. So this is a RIC spectra. Its intensity measured as a function of energy transfer at a particular momentum transfer or position in reciprocal space. And this lets us look at some elastic scattering here at no energy transfer, phonons at very low energy transfers, magnons or magnetic scattering at low energies here. Then as we move up in energies, we see these orbital excitations between different d levels and eventually charge transfer as we're moving electrons from oxygen to iridium. Okay? And if we vary the incident energy, we can go through these resonances, and we can use this to actually assign these different features to, not just the iridium, but also to different orbitals. Okay, so it's kind of a neat technique in that sense. So the first thing that we can do that's useful from this is to look at the electronic transitions, so looking at these orbital excitations, and we can assign these to an energy level scheme. Okay, so this is the scheme that we saw before from the effect of our crystal electric field spin orbit coupling. And so we've got what we expect to be filled J effective 3/2 levels, half filled J effective 1/2 level, these empty EG levels. And so these different features that we see in our RIC spectra correspond to these different transitions between these D levels. So what's important here is that the gap from the elastic line here to these features here, that tells us about the splitting between T2G and EG levels. It's about 3 electron volts. The splitting between the elastic line and these features here, that tells us about the splitting between the J effective 3/2 and J effective 1/2 states. So we're mapping out the energies of these electron orbitals, and that lets us pull out the energy scales associated with the distortion of the iridium 06 cage. That's this delta trigonal, the splitting that we see between the B and C peaks here, and the spin orbit coupling, which is the splitting between BC and =0. Okay, and so the fact that this splitting is much bigger than this one is a good sign that this J effective 1/2 picture is still relevant, even though we don't have an ideal crystal structure. All right. We can also do X-ray absorption spectroscopy. Again, this is another thing where we tune to absorption edges. There's different transition rules associated with these. And the important thing is that it gives us a way to map out the empty electronic states. Okay. And so if we look at where these electronic states are, we can compare different transition rules, so different absorption edges. So we get something that's called the branching ratio that gives us the ratio of these unoccupied states, how many states are available. Okay, and it turns out that we can relate this to the strength of the spin orbit coupling and pull out a measure of the L.S. This is the expectation value of the spin orbit. Okay, so in the case where we have negligible spin orbit coupling, this branching ratio, so the ratio of this intensity to this one, it should give us about 2. If we have this J effective 1/2 state, we expect to see a much bigger peak at the L3 edge and a little peak at the L2 edge. And so we should see a big branching ratio. And so if we look at some of these rhenium-based compounds, we see something looks pretty statistical. We move into these iridates, honeycomb iridates, layered perovskite iridates, different versions here. We get these big branching ratios that, again, are indicating to us that we have maybe interesting physics from this strong spin orbit coupling. All right. So the last thing that I said we wanted to check is if we could see evidence of these Kitaev interactions. Normally, the way we would do this is we would do inelastic neutron scattering, sort of the gold standard for trying to map out the terms in a Hamiltonian. But that's not really an option for us with these materials because they are heavily neutron absorbing and they tend to grow as very small crystals. So sort of micrograms or milligrams in size as opposed to grams. So we just don't have crystals big enough to do these inelastic neutron measurements. We can sort of make the best with what we can do. And so you can do some inelastic neutron scattering on powder samples. And I can show you some data here reported by an excellent group at Oxford. But this is, I would describe this as a spectrum that maybe only a mother could love. So you're supposed to believe this is a magnetic peak here that looks like this. You can use this data to maybe constrain the terms that might be in the Hamiltonian. But what we're going to try and do is use RICS to look at higher energy excitations to maybe probe different energy scales. Okay, so what we fight with RICS is that it's very difficult to get to very low energy things. And so we're going to try and use this neutron and X-ray complementarity. So the first thing we want to see is do we see a magnetic signal? And the way we determine if a signal is magnetic is, does it have the right energy dependence? Does it resonate as we go through this absorption edge? It does. Does it have the right temperature dependence? If we warm up, our magnetic peak should go away. It does. And does it disperse at all? And again, it's a little difficult to pull this out from the background, but we do get a feature that looks like it has momentum dependence too. So we have this feature that looks magnetic. We can then compare it to different theoretical models. So I'm showing you here sort of two simple models. The pure Heisenberg model, this one's got 3 different Heisenberg exchange terms for nearest neighbor, next nearest neighbor terms. And then one model that involves Heisenberg and Kitaev terms. And the big difference between them is this mode up here, this high energy mode that peaks at one position in momentum space that we call the gamma point. Okay, so you only get this high energy gamma mode if we include the Kitaev term. And if you compare this to the limited region in reciprocal space that we can map out with RICS, then this seems to match actually quite nicely to what we've seen here. So the fact that we see this high energy feature, even though it's right on the edge of our resolution limit, this suggests that we might have a Kitaev term here. So a few years later, the RICS energy resolution has improved, can go back and measure this again. So at the time we were using sort of world leading resolution, which is about 35 MeV. With new analyzers, you can get about a factor of 3 times better than before. And you can see that this feature really is real. It exists. The signals go way down once you start doing these high resolution measurements. But if you take the time, you can map them out. And you can compare this to those theoretical models again. And instead of just saying, is there a Kitaev term or not, you can actually try and put constraints on the size of these, whether they're ferromagnetic or antiferromagnetic. And so what we see here seems to be consistent with a ferromagnetic Kitaev term that is fairly large compared to these other interactions. Okay, so again, a good sign that we have something that looks Kitaev-like. I won't spend too much time on this except to say that there are many different ways that we can tune these systems to try and get them closer to this Kitaev limit. Pressure was one of the first that we looked at. So if you put these materials inside a diamond anvil cell, you can crush them to very high pressures, sort of 1 to 20 gigapascals, so many thousands of times greater than atmospheric pressure. What do we see when we do this? Well, we see the branching ratio responds. It's very sensitive to applied pressure, okay, drops off very quickly. What does the RICS spectra look like? We get a lot of splitting of these orbital features that we were looking at before. So the combination of these two results suggests that when we're applying pressure, we're basically destroying this J effective 1/2 state. So we make our structural distortions larger, and that gets rid of this, this nice balance of crystal field and spin orbit coupling. So we enter a new, more complicated regime. You can do synchrotron diffraction, so not resonant, just looking at the crystal structure. And what you find is a pressure-induced structural transition at about 3 gigapascal, where we see a lot of those orbital changes happening. We go from a low-pressure monoclinic structure to a high-pressure triclinic structure. And if you refine these powder diffraction patterns, what looks like is happening is we're forming these little dimers. So the hexagon starts as regular, and then it forms these little iridium-iridium pairs once you go up to high pressures. Okay, so this data is interesting. Also not a quantum spin liquid, but one which we still have a lot of different experiments that we can do. Okay, the other thing I wanted to talk about was non-honeycomb lattice materials. And so the first thing I'm going to show you are different materials based on a face-centered cubic lattice. Okay, so we've got 2 different materials that I'm going to talk about. Materials based on this crystal structure, double perovskite, and this structure here, which is an anti-fluorite crystal structure. Okay? And this is work that was done more recently with collaborators from Oak Ridge and University of Tennessee. Chung Chen is now a postdoc here in the Center for Crystal Growth upstairs, as well as Greg McDougall and Dalmau Reggie Plessy from University of Illinois. Okay. So I started out trying to convince you that what was important for these Kitaev interactions was having a really special bond geometry with these heavy atoms that gave us strong spin orbit coupling. But more recently, about 8 years ago, there was a proposal that you could also try and get to a Kitaev interaction using sort of a different design principle. So instead of doing directly edge sharing octahedra, you could have octahedra that had parallel edges, but some spacing between them. And so the model material that was proposed here was we call a 6H perovskite, this barium iridium titanium oxide 3129. And it was proposed that this could be maybe a triangular lattice Heisenberg-Kitaev material. And so the argument here is you still have iridium 06 octahedra, and now they're separated by some greater distance. And so you can still imagine the same exchange path argument between this iridium and this iridium. You can get an interaction along this path or along this path that can destructively interfere. But when you space out these iridiums more, you potentially weaken the normal Heisenberg interactions that would go along this exchange path from iridium to oxygen to iridium. And you also cut down on any direct overlap between the iridium wave functions. So in theory, this could give you a case where those Heisenberg terms are weaker, the gamma term is weaker, and maybe this gives you a chance to see Kitaev interactions in a different geometry. So for barium iridium titanate, this didn't actually work out very well. It turns out that the titanium and iridium are fairly close in size, and so they mix, and the site disorder prevents this from being a nice model triangular system. But it opened up this idea that you could get Kitaev interactions even without a honeycomb lattice. And so one place that you can go where you still have these sort of parallel edged octahedra is to the double perovskite structure. Okay, so this is another crystal structure we know and love here. It's really flexible. You can grow just a vast range of different materials where you substitute different A site ions, different B site ions, different B prime site ions. And so you get all of this space for chemical tuning. And again, if what we're looking for is big nearest neighbor iridium distances, these are over 5 angstroms, so there shouldn't be much direct overlap between iridium wave functions. So we expect small direct exchange and these narrow electronic bands that might help us get close to this ideal J effective 1/2 picture. So if you put something non-magnetic on the B site here, then you get a network of iridium 06 octahedra that you can map onto a face-centered cubic lattice. So the iridium octahedra is supposed to be the dark blue here, and they can be considered down here. And you get different Kitaev possibilities on your face-centered cubic lattice, shown here in the red, blue, and the green bonds. Okay, so we wanted to study a series of these different double perovskite materials. We picked this set of 4 because they gave us different degrees of structural distortion. So we can tune the spacing, we can tune the shape of the local iridium cage, we can go from monoclinic to cubic, we can put in a little bit of site mixing or a lot of site mixing and see how these things affect what we see in terms of their Kitaev properties. What we find is that these sort of subtle structural details don't really have much of an effect at all. So you can do the X-ray absorption measurements again, you can find the branching ratios, they're all very big. You can do the Rix measurements. You can find that the crystal field splittings are small compared to the spin orbit coupling. So that's the lambda and the delta that we pull out here. And so these are signs that this J effective 1/2 ground state is a good description for all of these materials. And then we can look at the magnetic structure. So here, the energy scales are low enough that we can't really do magnetic Rix very well. So we need some other route to try and guess at the interactions. And so what we can do is try and get at this indirectly. So we can solve the magnetic structure and then compare it to theoretical calculations. Okay, so these calculations tell you for different interactions what kind of ordered structures you expect to see. We go out and measure the structure. That should give us an idea what kind of interactions might be there, might be at play. So we've got this theoretical phase diagram for these double perovskites. It includes a Heisenberg term, a Kitaev term, and this gamma term, the off-diagonal exchange. And so you can see going up here, this is increasing gamma. Going over here, this is increasing Kitaev. On the plus side here, these are anti-ferromagnetic. The negative sign, these are ferromagnetic. And so we have a case where there's existing neutron data on powder samples that sort of limits the number of possibilities for the ordered state, but can't distinguish between them. So we can use these resonant magnetic X-ray scattering measurements that let us study very small single crystals because X-rays are very strongly interacting. We can find the magnetically ordered peaks. We can look at the azimuthal dependence of these peaks to pull out the moment direction. That lets us identify the magnetic structure and situate it on this phase diagram. Okay, so we've used spectroscopy to tell us that this J effective 1/2 picture is a good description. Now we use the elastic scattering to tell us what the magnetic structure is. And that gives us a way of sort of indirectly, at least, attributing this to an FCC Heisenberg Kitaev gamma model with an antiferromagnetic Kitaev term. We could do the same kind of exercise on the iridium halides. And so here, the anti-fluorite crystal structure looks a lot like the double perovskite structure, but you imagine that the B prime site there is empty. So you still get iridium octahedra. Now we're not looking at oxides, we're looking at chlorides or bromides. And so this is going to change the electronegativity here. And so we expect that to have an effect on the bandwidth. We also can play some different games with this structure. We can intercalate into the vacancies that we've got here. So you can get water in between these layers. And that gives you another degree of structural tuning. And so we looked at a series of these halides. So a chloride version, bromide version. We swapped out the potassium for ammonium over here. And then we have this sodium intercalated version here as well. Okay. So again, large branching ratio for all of these. Good sign for J effective 1/2 physics. What's really interesting is if we look at the RICs and we focus on the T2G excitations here, this looks like one little peak here, so we have to blow it up and look more closely. One of the things that's remarkable here is that the non-cubic crystal field splitting is very, very small. Okay, and it's very small even when we start to intercalate this system or when we play around with the size of the structural distortions. And so when you move from these oxides into the halides, into these bromide and chloride materials, these are the best examples of this J effective 1/2 ground state that we've seen to date. Okay, so very small deviations away from this J effective 1/2 energy level scheme. And again, not nearly as sensitive to the local structural details as we might have expected ahead of time. Okay, so you can do the same game, studying the magnetic structure, mapping it onto these theoretical phase diagrams. And as in the double perovskite case, what you get is something that looks consistent with an antiferromagnetic Kitaev interaction term. Okay, it's a relatively small energy scale. It's about 3 to 5 Kelvin, but it's not so different from the strength of the Heisenberg exchanges there. Okay, so in the time that's left, I wanted to say a little bit about the most recent thing that we've been working on, my group at McMaster. And this is whether or not we can find evidence of this Kitaev type physics in a different lattice geometry altogether, which is going from these FCC lattices to chain-like quasi-one-dimensional materials. So this is work that's really been led by Z, my senior master's student, who's in the back here. But she's also gotten help from the other group members. So Chung, who's in charge of the crystal growth lab, James Beer, who's helped with the magnetic characterization, and Daniel and Monica, who've helped with some of these synchrotron measurements as well. And of course, Jim, who's helped us with a lot of in-house structural characterization. So recently, there's been a fair amount of theoretical interest in what happens when we put these Kitaev interactions on low-dimensional structures. So people studying Kitaev spin chains, people studying Kitaev spin ladders over here or over here. But there has been very little experimental work because it's hard to find materials that seem to be suitable experimental model systems. So the best that we have to date is this material, which is referred to as a twisted Kitaev chain. It's a sort of cobalt niobium-based material. But we don't really have a lot of different model systems that we can look at or that might give us opportunities to start playing around with different kinds of chemical or other forms of tuning. So we decided to look for low dimensional iridium-based materials. And the place that we decided to start was calcium iridium oxide. So this 214, sort of a surprising low dimensional material. This is the same kind of stoichiometry as the layered perovskite iridates that seem to be analogous to high TC superconductors. But this calcium 214 was first reported in the 1960s. It seems to have everything that we want. So it's got the iridium, that gives it strong spin orbit coupling. It's got this quasi one-dimensional chain-like structure, which is edge-sharing iridium-06 octahedra that run along the C-axis. And so bond angles should be close to 90 degrees, which opens the door to some Kitaev interactions. If you look down at this from above, you'll see that these octahedra are sort of aligned in this kind of pretty pattern here. Spacing between these is fairly large compared to the spacing along the chains. Right? So this looks like a great place to start. The only problem is, although it's been reported and studied fairly recently, it does not seem to exist or grow. And Z spent a long time confirming that that was the case. So when you try to grow calcium 214, what you actually get is this calcium 5,3,12. So this is a version of 214 where we basically lose 1 out of 6 calciums. So it's a calcium deficient structure where you just basically knock out the calcium at this 0, 0, 0 site. Okay? So it looks almost the same, but in a sense it's kind of prettier. We get rid of calciums here and here and here and here. And again, still have the chains well separated. We do have some other structural things that might cause a little bit of concern. So these octahedra are not perfectly regular. They're distorted in both directions. So we get quite a range of bond angles here and bond lengths, a little bit away from the 90-degree angle. So we wouldn't expect this perfect cancellation of Heisenberg terms, but it maybe gives us a place where we could find some combined Heisenberg-Kitaev chain physics. Okay? The other complication, though, that we pick up when we lose some of these calciums is that now the valence is no longer this ideal 4+. So we don't just have iridium 4+, the 5d5 configuration that gave us these quantum spins. Now we've actually got 2 iridium 5+ ions for every iridium 4+ ion. So we have 1/3 of our iridium that have these quantum spins, 2/3 which are non-magnetic. Okay, so this does give rise to interesting physics in its own right. And so if you study these materials, there's a magnetic transition, looks like the formation of potentially one-dimensional antiferromagnetic order. There's also a hidden order transition at higher temperatures up here around 105. What this is actually is still, I think, a little bit debated. Is it some form of charge order? Is it potentially some more exotic form of multipole order? We don't really know for sure yet, but because of this mixed valence, there's actually quite a lot going on in this material, and not a lot has been done in terms of sort of systematically mapping this out and looking at how you can tune this material. So what Z did, actually a suggestion from John Greedon, who is seen in the audience here, was to dope this system to try and bring it from this mixed valence back towards the ideal 4+ state. So we did this by trying to incorporate yttrium into the structure. So putting yttrium, which is 3+, onto the calcium, which is 2+, to try and get towards this all quantum spin state again. And so we start out here at x = 0, this parent compound, where again, we've got 1 to 2, iridium 4+ to 5+. And we're trying to get to x = 2. That would be all iridium 4+. We haven't gotten there yet, but we have gotten over half of the way. So the highest doping that Z has grown so far is this 1.3 concentration. So that gives you 5 of these iridium 4+ ions for every 1 iridium 5+. So basically, we've increased the concentration of spins by a factor of 10 here. Okay. If we want to convince ourselves that the yttrium is actually getting into the crystal structure. You can do single crystal refinements. Looks like it's there. Looks like it's sitting on the calcium sites where we want it. You can also do these X-ray absorption measurements to map out how the oxidation state changes as a function of doping. We can do is compare to these reference materials, and the position of these absorption features is very sensitive to the oxidation state. So you can see that there's about a 1 electron volt shift as you go from the iridium 3+ to 4+ to 5+ oxidation states. So you can see our 5,3,12 parent compound sitting in here, about 2/3 of the way between 4+ and 5+. And you can see that the 1.3 sample is quite close actually to this iridium 4+ line here. Okay, so this is a good sign that we're getting close to the limit that we're interested in. We can also look at the magnetic behavior of these materials, and even without getting all the way to our 4+ limit, we can go from the parent compound, which shows this transition about 7.5, to our highest dope compound, which shows a transition which has been elevated up to about 12 Kelvin. Okay, so doping is increasing our magnetic transition temperatures. It's not doing much to our Curie-Weiss temperature, so the overall energy scale for these magnetic interactions doesn't seem to be changing a lot. The other thing that's jumped out here is that we have a previously unreported magnetic transition at lower temperatures here that seems to be really robust and reproducible, and also pops up at intermediate doping. So we believe that the phase diagram of this material in this system is really interesting, and there's a lot of different tuning that we still have time to go after. All right, so just to conclude then, hopefully I've convinced you that we can get sort of interesting magnetic behavior in these spin orbit driven materials, these heavy transition metal oxides. Particularly one of the things we can get here that we don't see in lighter materials are these bond dependent Ising interactions, the Kitaev interactions. So there's the possibility that these will eventually lead us to quantum spin liquids, although we're not quite there yet. So the first of these candidates that we looked at were the honeycomb lattice iridates. The best candidate actually that we've found so far is a ruthenium-based compound, ruthenium chloride. We can go on to other more lesser studied or lesser tread paths, looking at these FCC iridate materials or these chain-like materials. And I think there's still a lot of interesting work to be done on these. Yeah, so thanks very much for your attention. I'm happy to answer any questions you have. Yeah, thanks.
So a gate was a half spin chain system has a quantum liquid ground state anyway, right? So how would the chaos interaction make it a different type of quantum liquid?
Yeah, so I think my suspicion would be that it would be very difficult to get rid of that nearest neighbor Heisenberg term altogether. So I think what we would be hoping for is a Heisenberg Kitaev chain where you might get competition between the Heisenberg and Kitaev interactions. So you could frustrate the chains that way.
I'm just wondering if it's a different paper.
Yeah, so I suspect it would be. I don't have a precise model to point you to, but you know, I think the key for us is like you say, trying to distinguish one type of disordered state from another one. And in that regard, you really ultimately do want to get at the magnetic excitation spectrum, which is tricky at these energy scales, but not impossible.
Are there ladder type compounds that you can imagine that are known to exist with iridium, like there are, say, the glucose, you can make very nice 90-degree bond angle ladders.
So there's theoretical work on this Kitaev ladder, but not a lot of real materials that we think are close there. So I think that's an interesting direction we're hoping to get to, but we don't have the right material to work with yet. Yeah. And I mean, maybe I mentioned before that you can find ruthenium and cobalt-based materials that still have significant Kitaev terms. So that might be a route. You can find a ladder material in those lighter elements if you can scale some of the other energy scales, you still have a chance to get into the right regime.
Do you think there might be any iridium 4, iridium 5 ordering, or do you think they might?
So I feel like it has to order at some point. And again, my suspicion is that this transition around 105 must be tied to that charge physics. There's a change to the resistivity around there as well that suggests that something electronic is going on. But the structure is complicated, and there is recent synchrotron X-ray work that suggests that there's sort of a complicated distortion forming here. But whether that's due to just sort of a simple charge order, or whether it's this more exotic multipole order, I don't think people have really decided on the answer there.
Early on in your talk, you showed this color contour map of energy dependence of a whole bunch of spectrum.
Mhm.
And it looked like the low energy one was centered on a different energy than the other ones.
Yep, right here. Yep. So you're wondering about the sort of.
It's the incident energy dependence on that. The first one is at a different incident energy.
Yeah.
than the other one.
So this one and this one versus this one and this one?
Yeah.
Yeah, so that's the orbital selectivity that I mentioned. So the difference here in energy along the vertical, which is as we're scanning the incident energy, that's 10 dq. That's the difference between basically exciting your core electrons into the T2G levels, that's what you're getting here and here, versus going into the EG levels, that's what you're getting here and here. So that's actually really helpful when you're trying to identify what these orbital transitions are coming from. And if you have systems where there's different oxidation states, maybe you have iridium 4+ and 5+, you should also be able to separate out the physics from those based on the incident energy dependence as well. Well, that's a little trickier to do.
You mentioned that some of these materials you only grow really small crystals.
Yes.
So why is that? Is that a limitation of the material?
Yeah, it seems that they are just they're difficult to grow. So mostly we grow them with flux growth, which tends to produce smaller crystals anyway. The iridium is really expensive. So even if you could find a system that would grow well enough that you could try a floating zone growth, it would probably cost you about $10,000 worth of iridium. So it just seems like it's difficult to crystallize a lot of these materials and to grow them at size. Yeah. So we've gotten better. And the other thing I didn't mention is that one of the other things you can take advantage of is not just being able to see small samples and tiny crystals, but you can also look at epitaxial films with RICs. So you can do these inelastic scattering experiments on, tens of nanometers of material, which if you're thinking about this from an inelastic neutron point of view, would be impossible to get at. But sometimes you can use the epitaxial strain to stabilize some of these things that we can't grow in bulk. So that can be another useful tool at our disposal.
We should talk about them coming for an electron diffraction.
I'm sold.
You were looking at some double drops, right? But why is it well basically a lot of money and cubic, and of course in the cubic case you exactly 9 everything would have to be exactly 90, but not the case for the one. So but you didn't see any differences.
Yeah. So it's quite surprising. Because we had expected that this would be almost like a fruit fly experiment where we could look at the effect of these small changes in local structure on the RIC spectra. But the difference in this non-cubic crystal field splitting is very small and almost unchanged. And you can even look at, if you go from these double perovskites, some of these have structural transitions as a function of temperature. You can look at the high temperature cubic state, low temperature monoclinic state, and there's very little difference here. So we know from looking at other iridates, from looking at pyrochlores, that there are longer range crystal fields effects that can complicate things, that it's not all just the immediate iridium oxygen shell, but yeah, this one is still a surprise as to why there's not more difference between them.
Okay, that's, please join me in thanking Val.
Thanks, everyone.